Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Fikri bin Muhammad Raski, and I'm from Group PSP Power System Protection Group 12. Okay, for our title is Exploring Neutral Grounding Methods in Small Networks. And my group members is Yik Zhu Yuan, Arif Hidayah bin Ahmad Arifudin, Muhammad Zarif bin Ziman, Muhammad Faizal bin Isman, and me, Ahmad Fikri bin Muhammad Raski. And our lecturer's name is Dr. Muhammad Alfa bin Muhammad, Dr. Fatih bin Muhammad Nur, and Dr. Abal.
For the introduction, a comprehensive network known as power system facilitates the generation, transmission, and distribution of the electric power. The key component includes power generation plant, transmission line, and control mechanism, utilizing advanced technology for efficiency. The system caters to residential, commercial, and industrial users, aiming for a balance between generation and consumption. The protection delay plays a crucial role in responding rapidly to fault with requirements such as reliability, selectivity, sensitivity, and the speed of separation. The ultimate goal is to safeguard equipment, prevent damage, and enable the affected part of the system to continue operating smoothly. Protection delay must respond rapidly and effectively to fault, requiring reliability, selectivity, sensitivity, and speed of separation. Relay remain inactive under normal conditions but respond promptly to fault using appropriate mechanism. Selectivity emphasizes operating promptly and selectively in response to specified ground condition. Grounding or earthing is fundamental for connecting electrical system to ground, enhance safety, and prevent hazard. Grounding plays crucial role in preventing equipment damage, facilitate the safe dissipation of electric fault. Neutral grounding methods such as solid grounding significantly contribute to the overall reliability and safety of electrical system.
Okay, we go to the literature review. Okay, first, the importance of neutral grounding. Small networks, like those in residential and commercial buildings, rely on neutral grounding techniques for stability and safety. And the factors influencing choice is the chosen grounding strategies impact depends on factors such as network type, voltage level, fault currents, and equipment sensitivity. And the grounding strategies and trade-offs. Solid grounding provides quick fault detection but poses risk. Resistance grounding level lowers fault currents but has drawbacks, and the reactance grounding suits long connection but involves complexity and potential resonance issue. Optimal approach and empowerment. The best neutral grounding technique balance network stability, equipment protection, safety, and cost. Engineers armed with knowledge of trade-offs can make informed decisions for the secure and reliable functioning of small network systems.
For the problem statement, the challenge is identify the most effective neutral grounding strategy for small-scale industrial power system. The method used is solid grounding system and resistor grounding system and reactant grounding system. The solution is address uncertainties, enhance system reliability, minimize fault rate, and improve system stability. The balance is to ensure safety, equipment protection, and continuous service in small-scale industrial network. Objectives. The first objective is to evaluate the performance and safety implication of different neutral grounding methods, including solid grounding, resistor grounding, and reactant grounding in small-scale industrial power network. The second objective is to investigate the economic consideration and impact on equipment reliability associated with implementing specific neutral grounding strategies to provide practical recommendations for optimal performance and safety.
Assalamualaikum, my name is Muhammad Faizal Osman and I will present about the methodology. Okay, on the slide has various type of neutral grounding. First is solid grounding. The principle is neutral point is directly connected to earth with minimal impedance, and result is in the highest fault current but offers the fastest fault detection and clearance. And for the advantages, it's a simple design, easy to implement, efficient fault detection. And the disadvantages is high fault current can damage the equipment, can increase the fire risk, and cause tension over voltage. And for the second neutral grounding is resistant grounding. Resistor inserted between the neutral point and earth, limiting the fault current to a safe value, provides a balance between rapid fault detection and reduced fault current. The advantages is lower fault current compared to solid grounding, protects equipment from overcurrent, and allows for selective earth fault protection. And the disadvantages is increased power loss due to the resistor and more complex design than solid grounding. And lastly is the reactance grounding. An inductor is inserted between the neutral point and earth, limiting the fault current predominantly to the capacitive component, useful for system with significant cable lengths and capacitance. And the advantages is it can limit the fault current, minimize the ground potential rise, and suitable for long cable feeders. And lastly, the disadvantages is the higher cost and complexity compared to other methods. Potential for resonance issue. Okay, for the software that are we using for the project is ETAP, because the ETAP software can provide comprehensive analysis capabilities, including load flow analysis, short circuit analysis, motor static analysis, arc flash analysis, harmonic analysis, protection coordination studies, and reliability analysis. It can aid in creating effective power system, analyzing performance, increasing operational efficiency, and making informed decisions. Okay, in this slide is the small network model for the project. Okay, on this slide, I will explain you about the effects of the neutral grounding method. First is the effect of solid grounding method. It has fast fault detection and clearance, but high fault current. It increases the equipment stress and fire risk, and can cause transient overvoltage and be sensitive to harmonics and unbalanced loads. And the second one is resistor grounding effects. It limits the fault current to safe level, protects equipment and allows selective fault protection, and can cause power loss and delay fault detection. The third one is reactance grounding effect. It limits fault current, protects equipment, and reduces fire risk. It also minimizes ground potential rise and has lower fault clearance.
For the simulation, we use three-phase and connect to bus, connect to transformer and bus. For the voltage as the bus 3, we use 110 kilovolt and transformer step down become 11 kilovolt. From the simulation, we can find solid grounded system, resistor grounded system, and reactor grounded system.
So this is the result from the simulation in ETAP software, which is we have three: solid grounding, resistor grounding, and reactor grounding. So each of the result contain voltage factor, peak value, current in the steady state, contribution of the each phase. All these things considered, the figure point to a severe short circuit on the three-phase system. Both of the protection device, tripping, and the large reduction in the voltage on the faulty phase were produced by the short circuit. So the conclusion of this project is to provide insight into a possible large-scale distribution network by showing a power system using transformer T2, effectively reducing the high voltage of 110 kilovolt to a more manageable 11 kilovolt. The transformer powers several substations and eventually the nearby houses and business. The significant apparent power flow of 7,621 MVA underline the vital function of T2 in the system, maintaining smooth and dependable transmission of power across the network. Although more information is required for the true understanding, this initial look at the project indicate the crucial and well-designed piece of infrastructure that powers our contemporary world.